this is an interesting reaction. It's a base-promoted reaction. The base increases the rate of the reaction, but it's consumed, different from a catalyst. Right, so remember, catalyst increases that rate, but is not consumed. When a reaction is promoted by an ester base, a full equivalent of the ester base is required. So we're going to look at case 1 down here below, which is base-promoted. So first step here is we have alpha positions, right? So here's your alpha position. Now we have 2. But they're equivalent to each other. If they weren't, then we have other things to consider. We'll take a look at that once we're done looking at this first step. So we're going to come around here and we're going to grab that H, and that's going to do this. Right? So for the sake of saving time, here is our enolate, and of course that has resonance. So we could draw the resonance structure of this, right? Now what happens next is that we have our negatively charged carbon come over and grab a hold of one of our chlorine atoms. Now remember, and we can build off of previous knowledge a little bit here, that carbon right there is currently sp2 hybridized. Right? So when it changes to sp3, we have the potential to form stereocenters, right? So remember that it's that p orbital, and I'll kind of draw this like slanted in here. It's that p orbital. It's really in and out of the plane of the page that's reacting. So if that front p orbital reacts, then what we end up getting here is our chloro group on a wedge. Right? If the back p orbital reacts, then the chloro group is on a dash. So in this case, you get a mixture of enantiomers. Now, one of the problems here is that this reaction is easily polyhalogenated. So chlorine in the presence of hydroxide and water easily gives you the tetrachlorinated product. Now for our class, we will just monohalogenate. So as far as predicting products and stuff like that with your homework and your textbook and exams, that's what you want to write as your products. Well, let's look at an example, guys. This will be good for us. A little review of the past lectures here too. So why don't we start off with this? Let's take that same cyclohexanone and let's put a methyl group at that position. So I want to come up here and I want to do this. I want to do step number 1, LDA, and I would like to keep the temperature cool. And then down here below, I would like to add hydroxide and crank up the temperature. So when we do that, let's think about what happens. So LDA, lithium diisopropyl. Remember, it's a big base. It's large and it's strong. And in this situation, we have irreversible conditions. So what happens is that LDA comes over and it deprotonates here. We'll call this alpha 1. It deprotonates at alpha 1. So what we're going to get is our enolate intermediate, right? And I'll just write here plus resonance. Okay? And then what would happen if we did a chlorination? So we'll go through here and let's add chlorine. Right, so with chlorine, we're going to react that, of course, at this position. So you have your 2 chlorines together. We're going to grab that chloro group and kick that off. And then same deal, we get that on a wedge, right? At this position, that shows up on a wedge or a dash. So you would have your chloro group out like this. And then your chloro group back like that. All right, now, in this case, what's the relationship between these two? Well, because of that methyl group, these turn out to be diastereomers of each other. Now, that alpha 1 position is more easily accessed, and because of that, this is what we would call our kinetic product. Sometimes they'll say it's kinetic control. All right, So with hydroxide, high temperature, those are reversible conditions, right? So what happens is, right, remember we go through that whole pathway where we form the kinetic, then we come back and we form our original keto form, and then we form the thermodynamic enolate. So what that means for us is that we're going to form this. Okay? Right, and the idea behind that, if you recall, is when you look at that resonance structure, with a little minus there like that, that resonance structure is the most stable of your kinetic and your thermodynamic enolates. So it leads to the thermal product. All right, so then step number 2 here. So here's our step 1. Again, that's your step 2. So our step 2 here, adding chlorine. And we're going to come around and we're going to grab that chloro group just like so. And then we're going to have a mixture of stereoisomers there. So we're going to get our carbonyl with a chloro group plus our carbonyl with our chloro group on a wedge there. Right. And again, because that came from the most stable, thermodynamically stable enolate, this is the thermo product. All right, guys, in this next section, I want to look at alpha halogenation, but under acidic conditions. And under acidic conditions, this is a catalyzed reaction. So before, what we were talking about was the acid or base promoted halogenation. So we see base promoted, right, and acid catalyzed here. So there can be reactions that are acid promoted, but in this case, it's acid catalyzed. So let's take a look at the mechanism. So what we're going to start off with here is a keto. Start with a keto form here. So there's a preliminary step here, and what has to happen is that this needs to form the enol. So we have to start off with this. So I don't want to write out that mechanism, but the reaction conditions here are H3O plus, or H2O and H plus. So again, here we have acid catalyzed, right, keto, enol, Tautomerism. All right, so we see the conditions H plus, H2O, and we see chlorine in here too. So then once that keto form turns into the enol form, that enol form will then react. It's going to react with chlorine. So here's our Cl2 with our chlorine. And here's what happens. So we're going to take a set of electrons here, pull them down, and then we're going to swing around and grab a chloro group. All right, now when we do that, we're going to have a potential stereocenter forming right here. So what we're going to form is our oxygen, right, double bound here, and then we're going to get a chloro group here, and then we're also going to get down here, I'll write it down here, the other flavor of this thing, which is the chloro group on the dash there. And here's the catalyzed part. So here we get H2O coming in. So now water's going to swing around and grab the H, right? And it's going to do the same thing down here below. I'll leave the arrow out for that one down below. So what we get here is our carbonyl with our chloro group on a wedge, and then our carbonyl with a chloro group on a dash. So just a little note here, it says acid catalyzed works for ketones only. So it turns out that this reaction, if you try to do this reaction with aldehydes, aldehydes are easily oxidized to just form carboxylic acids. So the reaction doesn't work really that well. You can see that written down here below. So here's your aldehyde, bromine, water. You got your carboxylic acid on this thing. All right.